Welcome! I'm Simon and I will teach you quantum hardware design. In this video, we will take a look at traveling wave parametric amplifiers. Structure of this video is theory. It's 30 minutes, introduction to quantum hardware parts and just a theoretical background regarding um, traveling wave parametric amplifiers. Then we will move to the design stage where we will do layout and simulations. Here are amplifier applications. Most common is quantum computer, but there are also applications in dark matter detectors and astrophysics detectors. So very interesting. Mm. So there are different types which might need to use traveling wave parametric amplifiers. The main type is superconducting technology, but this can also be used in spin qubit technology since it is also cryo technology and it also requires some additional readout. So it can also be integrated into spin qubit technologies for some minor stuff. So here's quantum computer architecture. It starts with QPU, which is a quantum processing unit, which sits at a 10 millikelvin cryo level. Then there is a traveling wave parametric amplifier, which can also be at 10 millikelvin level, which is quite typical because it requires the same cooling as mm, quantum processing unit. But sometimes it might be even uh, at a little higher levels, something in between 10 millikelvin and 100 millikelvins. So even 100 millikelvin can be fine for traveling wave parametric amplifiers. It quite depends. Uh, so this is quantum computer architecture. In higher levels, there are RFIC or HEMT cryo, classical CMOS amplifiers, and then there is control electronics, which is at room temperature. So there is a picture of traveling wave parametric amplifier. You can see two ports, meander and cells, which includes resonators and juices and junctions. Here's nonlinear oscillator, which is important for understanding juices and junction effects, but it is more uh, relatable to QPU design or qubit design, but basically can see that the difference between normal oscillator with inductor and Josephson junction is that it requires infinite energy to reach higher levels with normal inductors, and Josephson junction is superior in this case. So for kind of traveling with parametric amplifiers, we don't use this kind of type of circuit or wiring. It is in series, so it is kind of superconducting bridge between the resonators, like here. So it is in series, and it kind of makes the connection with zero impedance. Um, so here's a slide with different types of amplifiers. The first type is Josephson parametric amplifier. You can see the circuit here, which is basically resonator cells and one Josephson junction in the end with bias or just inductor, or you can pump the signal here and adjust the juice junction. Here's a zoomed cell for juices and parametric amplifier. So this is the first type. This is a very simple one, and it is basically tuned at one frequency, at one resonator frequency. Uh, and there is another type, which is traveling wave parametric amplifier, which is more advanced type, which requires probably thousands of different or thousands of similar cells, whereas inductor and capacitor and Josephson junction in series. So this is a one cell, and you can see the zoomed fabrication cell here. So you will have uh, thousands of these. So it's way more complicated, and you can adjust frequency by tuning current of the Josephson junction and parameters of these elements. So here are lumped elements. There is some. This is more towards qubit design, but it also applies to traveling wave parametric amplifiers, since we will need coplanar waveguides for this, and there is kind of schematic for coplanar waveguide. This is qubit, and this is a resonator cell. We will use the similar design of resonator cells for our traveling wave parametric amplifiers. The only difference is that this is representation for coplanar waveguide, and for in our case we will use coplanar waveguides plus the kind of elements like real inductor shapes, and for capacitor we will use planes, because we will need higher values for capacitors. So there are different types of signals we will need for our traveling wave parametric amplifiers. There is a pump signal, the output signal, and the idler, and you can see the dependence of each signal on the gain or kind of behavior of the amplifier. You can see that by adjusting the um, the idlers and pump signals, you will get different charts for gains. Typically, this is the chart for S like S21 parameters of amplifiers gains. Yeah. There is also a very important element for traveling wave parametric amplifiers, which is Josephson junction, which is superconducting element. So here is a zoomed Josephson junction under microscope. This is how it looks like when it's fabricated. You also need air bridges, which are these little components which can be used to kind of shield the path for traveling wave parametric amplifiers. So this is one thing which can be used for amplifiers. Also the coplanar waveguide, which is the line here. You can see the representation of the line in the middle here in circuit elements, which is inductor and capacitors, and its impedance should be controlled, which is typically 50 ohms. Mm. So you can see the port, which is very important for connecting amplifiers with outer world. So this is the component here. We can play with the mm, port sizes, and we can also adjust the shape a little bit so it will be more convenient for wiring and connecting it to the mm, control electronics or the other parts of the quantum computer. So here's zoomed cell. This is kind of Josephson junction for Josephson parametric amplifier, and here's kind of a cell for whole cell for traveling wave parametric amplifier, the more advanced brother of the amplifier series. You can see Josephson junction and capacitors and inductors. This is the whole cell uh, for the one piece of traveling with parametric amplifiers. We will have thousands of these uh, little devices in our amplifier. Uh, we might also use interdigitated capacitors, but more commonly it is used just a big plane which will act as a capacitor. So in some uh, scenarios you might use interdigitated capacitor for traveling wave parametric amplifier, but oftentimes it's just plain. So here is on-chip inductor and spirals, which is also very important component for creating one cells, because we need to create resonator, and in order to create resonator we will also need some inductor, and to create inductor with higher inductance we will need to use spiral, and this is just a small on-chip inductor. So very important stuff for our amplifier knowledge is understanding S parameters and impedance profiles. So this is basically our device. This is our amplifier, and we will have some input, which is here. This is input side, and there is output side, and our device is here, and the S parameter basically tells us the gain of the amplifier or the reflection of the amplifier. So for this is S1, and this is S2, and we will basically probe the input against output to get the gain of our amplifier, but by really measuring these S11 parameters, which is these two, we can also get the reflection of the amplifier. So it's important to really understand these kind of parameters and S matrices, which tells us the properties of our amplifier. Really, yeah. We can really measure this stuff with precise and very specific instruments called vector network analyzers. Uh, yeah, so this is as parameters. Impedance profiles just tells us different properties for amplifiers, and these are important too. So here's Smith chart, which tells us kind of impedance uh, profile of our amplifier. So here's a chart which is circular, and on uh, like each side has different meaning. Left side is a short circuit, the right side is open circuit. When we go upwards mm, with our kind of mm, line, or with our um, measuring tool, we will get inductive profile, and when we uh, mm, move lower, we will get capacitive side, and the final kind of mm, measuring profile looks like this, which is a line with mm, different frequency sweeps, or with frequency sweep, and there's like frequency of let's say 100 megahertz, and it ends with the 10 gigahertz, and there's the whole trace uh, how our device uh, behaves across different frequencies. So this is also very important to know for amplifiers. Are kind of impedance profiles, and its tuning and characteristics. So there are different types of amplifiers. This is the main type, juices and traveling wave parametric amplifiers. Uh, yeah, juices junction and resonator cells, and there is thousands of these, probably 2000 or so. Uh, and there's different type, which is juices and parametric amplifier, which is very simple. You will only have some uh, gate input capacitor, which is here, and then you will have meander, and there is only one juice and junction, and there's connection to other meander side, and the meander basically tells us the frequency of our amplifier, and this is a very simple one, and it is tuned at the only one frequency. There's a different kind of topology for traveling wave parametric amplifier, or different style, but it is quite similar to the first one. It just uses different kind of arrangement of the cells, or it just plays with different types of uh, cells. Mm. So there is our traveling wave parametric amplifiers. You can see the zoomed one cell here. You have juices and junction here. We will need to take a look at the current of the juices and junction, and also capacitance of the juices junction. There is one big shunt capacitor, and there is a coupling capacitor for the resonator, and there is resonator or resonance inductor and resonant capacitor. Uh, by adjusting these values of resonator, resonance capacitor, and inductor capacitor, we will get different frequency. You can see that each color of the components represents the different layout component here. So the big shunt capacitor is yellow, it's here, and mm, the coupling capacitor is purple, which is here, and the big resonant capacitor is green, which is here, and the inductor is orange, which is just a small spiral here, which is here, and the Josephson junction is the element which connects the um, the different cells. So there is superconducting link or connection between different cells, and we will have probably 2000 cells, and this is our amplifier. So here is kind of circuit for different type of amplifier and kind of dependence of a turning on and turning off pumping signals. So there is so it's you can see it's frequency dependent. Turning on and turning off pump signals. You can see the impedance profile or resonant frequency for each resonant cell. So there is frequency dependence on resonant cell. There is breakdown of Josephson parametric amplifier. There is simple capacitor. This is zoomed capacitor here, and there is squid or Josephson junctions here, which is the active elements for Josephson parametric amplifier. And there is circuit, there is input capacitor, and there is one resonant cell which connects to the Josephson junction, and there is inductor which is here, which is used for kind of tuning the Josephson junctions and pumping the signal to the Josephson junction. So there is only schematic, which we already explained in the previous slide. So there is dependence of flux on a frequency. It's quite interesting to see the different flux modes. So there is gain for Josephson parametric amplifier, and you can see it's fine-tuned at the only one frequency, and it is very narrow within a few tens of megahertz. So this can be frequency at, let's say, 4 or 6 gigahertz typically for juices and parametric amplifier, and it is very narrow. Mm. So there is detail for one cell, and um, really measuring the resonant frequency of the cell. The resonant frequency is typical, uh, typically like this. I think um, it's around 7 GHz. Yeah. Um, um, so so there is um, there is a chart for added noise of an amplifier, and you can see mm, the different noise levels with kind of pump signal on and pump signal off. You can see that with the pump signal off, we will have very low noise, which is basically the noise from the previous device, which is the RFIC amplifier, classical ham amplifier, which is very low, but also the signal we need is also very low. If we turn our pump signal on, we will get a higher level of our noise, but we will also get the higher signal uh, for output, and uh, yeah, I think it should be. Um, um, yeah, so there is flex bias for Jefferson parametric amplifier, and you can see that by adjusting flux, we can adjust the frequency. So there is this is basically a coplanar waveguide, or our transmission line, or our meander, which can be represented by this schematic symbol, but also we can break it down into lumped elements, which is capacitor and inductor. And there is our Josephson junction, and there is our DC flux bias and our pump signal. And by really changing the DC flux bias, I think we can change the frequency of our um, of our mm, parametric amplifier. Mm, so there are different types of signals we will have uh, mm, in our amplifiers. There is idler signal, and there's the main signal and the pump signal, which is typically um, higher, and there should be our uh, I think resonant frequency, if I'm right. Um, so this is the breakdown of different signals in our amplifiers. Uh, so there is quantum chip workflow for our parametric amplifiers, which is very similar to the qubit and quantum chip design. We started with concept, and then we will move to the lumped elements representation. Then we will do circuit simulation. And once we are confident with our circuit simulation, we will move to the layout, and then we will do post layout simulation, so we know that the layout really matches our lumped elements and circuit simulation, and then we can do fabrication. For concept and lumped elements and circuit simulation, we can use some microwave studios, and typically for the bare concept phase, we will need to use some tool like Josephson circuits in Julia, where we just define our values and we will see our plots, like charts for amplifiers. Then we will put this into the microwave studio, where we will add our lumped elements and we will do our circuit simulation. And then layout, we can do it in Qiskit Metal or either key layout, and the FEM simulation in some FEM tool, whatever you will uh, be satisfied with, or you're confident with. And then fabrication. So here are different circuit simulation tools. The first one is Keysight, which is paid and very strong environment. Then we will have Josephson Circuits, which is just GitHub package or Python package. Uh, it is written in Julia, I think. It is free, lightweight, and it is just for prototyping and for very simple demonstrations. And there is AVR, which is paid and very good, but there are some models missing. So you have to choose carefully. There are different types of FEM simulation tools, which is ANSYS, which is paid and very strong. Then there is Elmer, which is free, lightweight, but still very good. You will have less tutorials and less support and less people using it, since it's just a free and open source tool. So uh, so Elmer is still really good, and there is POS, which is developed by um, Amazon, and it is cloud service and very good as well. You will have a lot of people supporting this, and you can see a lot of people working on integrating other tools with POS. Very nice as well. Then we will have FEM simulation types for our uh, amplifiers. We will have impedance and scattering matrices, like impedance and S parameters, and this kind of stuff. And then we will have EPR for Josephson junction and electric fields for Josephson junctions to really evaluate the Josephson junction. What is really um, kind of good thing to do is to really try to simulate only one cell in FEM simulation, because it's nearly impossible to simulate 2000 cells at once. There is not enough memory and computational power in modern laptops or desktop computers, so it's, I would say, required to simulate only one cell. And then we will have some capacitance and inductance mm, inductance parameters we will need in order to evaluate our components modeling in our key layout. Um, to match the circuit simulation and our concept phase when we already designed our uh, amplifier. So here are some pictures from design phase. This is the one cell for our traveling wave parametric amplifier. There is capacitor, and inductor, and the juice and junction, and the kind of capacitors to connect each juice and junction. Uh, So here are some plots for our amplifiers. We can modify the parameters of our elements like inductors and capacitors and even currents and the frequencies of signals we will pump and we will put into our amplifiers, and it will generate the output plot and the other uh, plots for our amplifiers as outputs. Here's plots for um, capacitive simulation. We will basically assign uh, some we'll just simulate the capacitors in our FM simulator to know the values and if the dimensions are really correct. Uh, so the fabrication materials are quite similar as for quantum chip design. Mm, so there is some substrate, some metal, and some insulating layer for Josephson junction, and this is basically it. That's right. This is the fabrication process. We will do spin coating first, then exposure uh, to uh, to mm, the light, which is made with very precision lithography machines. Then we will do development of our chip, and then we will do etching. And once we are done with etching, we'll move to coating, and then we'll do metal fill. Um, so this is the process for chip fabrication. There are different fabrication foundries which support superconducting design. You can either go with mm, some very well-known foundry, uh, which is major player in the industry like Global Foundries and Skyward, or you can go with your university fabs or uh, the smaller fabrication houses uh, near universities and institutes to fabricate your quantum chips. It will be cheaper and probably faster, and it will allow for uh, very precise tuning and faster kind of prototyping and fabrication. So this is our tasks, the papers we will need to follow. We'll take a look at them very shortly. So this is the end of the theory part and presentation part. We'll jump into the papers part very soon. So, if you like my presentation, please feel free to reach out. You can either send connection request on LinkedIn or send me a mail here on Gmail. So let's move to the other part. So here's our paper for traveling wave parametric amplifiers. We can see more details here, it is made for 20 superconducting qubits. Uh, its capability is to read out 20 superconducting qubits. We can also see the quantum efficiency of 75%. There is also a little about noise and gain and frequencies. Here is a picture of fabricated traveling wave parametric amplifiers and zoom out cell components and circuit representation. Here we can see current for, important details regarding design uh, parameters for each elements and components. So here is current for each Josephson junction, which is 4.6 microamp, and there is capacitance for Josephson junction, which is 55 femtofarads, and also other capacitances. And the important one is resonant capacitance, which is quite large. It's 6 picofarads, and also there is inductance for resonant inductor, spiral inductor, which is here, the orange line. And this should be it, design parameters. And if we scroll down here, there is a connection of our traveling amplifier. This is how you actually vary it, and there is some chart with gain and frequency. So here's our frequency. It goes from 4 gigahertz to 10 gigahertz and up to uh, 30 decibels. So here's our plot across frequencies. We can see some mm, um, gains at specific frequency. You can read it here. There is a very there are a lot of specific details regarding frequencies and stuff like this. You can quickly scroll through this, and here is our connection of traveling with parametric amplifiers into actual quantum computer. Here is our qubit, which we will try to read out. Here's readout connection into isolator, then directional coupler. Here's our pump signal for traveling with parametric amplifier, and here's our readout signal. And here's our traveling with parametric amplifier, and there's isolator, and it goes into HAMT, which is next cryo stage, um, which is above probably 100 millikelvin, I think, or 100 or above. So here's our HAMT RFIC Creo Classical CMOS chip. There is very little useful details. We can jump into our Josephson parametric amplifier, which is flux driven. There is a little theoretical background and introduction. We can skip this and we can move to our schematics. So it's flux driven, so there is our DC flux bias, uh, which we can tune our Josephson junction. Here is our pump signal, and here is our meander, which we can substitute with transmission line symbol, so we don't have to care about lumped element representation. And here is our dependence of frequency on flux. Here is our uh, schematic of or connection of our quantum computer, including cryo stages. And there should be little information about frequency of this amplifier. We can probably read it here somewhere. Next, we can move to our actual design stage. This is our circuit simulator for amplifiers. It's called Josephson Circuits. It's a Python package written in Julia. You can just install Julia and run this package. There is a lot of different supported designs which we can modify. The simplest one is the first one, and there are other designs which we can run, more complex ones for traveling with parametric amplifier. We will only do Josephson parametric amplifier, so we can copy this and we can copy it into Jupyter notebook. So here's our code. We can quickly run it, and we first need to install Josephson circuits. So to do this, we need to run our Julia, and we will just simply copy these commands. So now when we have our Julia Josephson circuits installed, we can jump to our Jupyter notebook and we can run our example. So this is our code. We can click Shift and Enter, and it will run it. It will generate gain plot for Josephson parametric amplifier, and here's our plot. This is, I think, the only chart we can get for Josephson parametric amplifier, but it is fine. We can see quite a narrow gain kind of amplified signal or peak. It's tuned at 4.65 gigahertz, and it's nice. Now we can take a look at breaking down our circuit or code. First we have variables, and the variables tells us the kind of composition of our circuit and the components we have. So we have port, we have resistor, capacitor, and inductor, and these values just tells us kind of rotation of our circuit and connection to other components. The first parameter is name, and the other parameter is the actual component. Next we have our values, which we can change, and depending on this we will get different frequency of our gain plot. You can see that this is a very major change, so we can um, maybe fine tune the other values. Uh, you can see that it actually works. Um, um, we can really open the uh, resonance calculator, online calculator, and we can pass the values in it, and this way we can actually calculate mm, the real frequency. Here we have uh, of input signals and frequencies. We can change the frequency by changing this number, uh, and this is really it. Um, Next we have these two parameters, and I think by changing this we can really change the kind of shape of the input signal. And then we have plot, which is actually. And then we have a plot where we can change the attributes of this chart down here by changing values like label. We can really change the label of the trace, which we can just change to trace. We can change um, the naming convention um, for, for our um, horizontal and vertical lines of our chart. So frequency. Um, so this is our modified plot. We can also play with the parameters here. I'm not quite sure uh, what this is all about. So the most important parameters are here. Now we can start designing our Josephson parametric amplifier. For this we will need a library called Q circuits, and we can see the elements here by tapping the libraries. Drop down menu, and we will need to pick a chip library, I think, and we will choose chip icon. We need to zoom out, and we need to press not sure which kind of symbol. Oh, me. Oh yeah, star symbol. Mm, and now we can start adding our um, elements. We will need a launcher, so we will click on launcher, and we can open the menu and really modify its parameters. For position, uh, rotation and angle, we choose some values. For position, we will choose let's say this value, and for Y position we will choose 5000, and for rotation we will choose uh, yeah, this should be about right. We need to um, let's say, okay, so probably no, not quite sure. This should be probably the right value, or maybe just 9,000. Okay, so probably different value. Yeah, 8,500. So we have our launchers. Now we will need to add meander. Okay, so now we need to add meander. We can do simply by choosing meander here and clicking. We need to set a proper location, which should be probably 2000 if I'm correct. No. Let's say 2000 and no. Maybe this should be right. And now we need to change the I, Y. No. Let's just say 5000. Yeah, this should be right. Now we need to click at the end here and change the coordinates here, which should be probably 4000. And now we need to adjust length, which should be probably 9000. Yeah, this should be right. We can also set, let's say, 17,000, and by clicking here and or let's say 17,000, and by clicking here at the end we can also, this is all too much, we need probably or 4015, and now we can just change it to, let's say, 30,000, and for meanders we just say three meanders, or 6 meanders probably should be right. So this is our first meander. Now we need to add the other side, which we'll do by simply adding a waveguide straight. We need to modify its values to, let's say, 8000. Is this correct? No, it's not. Uh, um, now we can really modify the length, which should be probably 1000, but the other way, so we need to flip it, which we can do by rotation 100, or maybe simply by mirror. No, 100 should be right. Okay, so let's see. This is a reference. So we'll need to add curved. Curved will be divided by 2 and rotated by 90 degrees. Let's say 5000 or not sure. Okay, that's not the correct one. Okay, so now we have our curved, and now we need to do straight again. The straight should be probably 7000 or 7500, let's say. Not sure what's the location here. We can probably measure the or somehow find out the coordinates for this. I'm not quite sure how to do it. So we can simply do this by choosing the cross, and thus we can know the coordinates. So the coordinates should be like this. So it's 6900 and 4900, and we need to set the rotation for 90 degrees or 270 degrees. And now we can set the length for this, which should be probably 1000. And now we need to do the same with the cross tool, and we need to set the or we need to choose the curved, rotation 180 degrees, and change the location. rotation should be like this, plus probably uh, okay. Maybe the length should be a little bit more. Or turn radius probably. Turn radius might be like this. Now we need to modify it accordingly. So like this. Oh. No. Oh. Now we need to add a straight one, which should be like this. Again, 90 degrees. And I think it should be this should be about right. And now we need to just adjust length, which should be 1000 if I'm correct. Wait a minute. 1500, let's say. Now we need to add Josephson junction, which should be in a junction library, and it should be probably simulation one. And this is our Josephson junction. We can simply rotate it by 90 degrees, and I'll select the move tool and move it here. For the we'll need 5000, so we'll say 5000, and for this we will say just like this. Now all is left to do is we need to select the end and adjust the end, which should be let's just I can't select it. The end should be the proper value should be here, which is Uh, so this is our kind of adjacent parametric amplifier. We can click and save it. Uh, and we can save it as a GPA. The parameters here are, I think, about quite okay in default setting. So we can click OK. So this is our amplifier. Now we'll need to export the XF files for FEM simulation. We can do this by simply clicking hide all and then um, choosing which one we will want to show, and this should be I think this should be quite okay, I think. So now we can click save as and export it as DXF files. We call it GPI. We will need to click visible layers only, and we can export it. Now we can move to really simulation. We need to click new project and click new HFSS simulation. Now we will need to import new our file. So we just click open our saved DXF file. It will only import geometry of our Josephson parametric amplifier. Now we need to really now we really need to do some finer adjustments. We will want to select our trace and also the other one, the other side, and so by clicking this and clicking shift we will expand, or let me Okay. So now we will click Unite, and this is one shape. We can click Edit and Properties, and or just by clicking this we can rename this and call it Trace. We will assign boundary and perfect conductor, and um, um, now we need to add our silicon box. We click assign material, we click silicon from system materials, and click add. So this is our silicon, and now we can really um, we can move it. We'll need to change transparency to fully transparent, and we will leave it as a vacuum. Now we will need to assign ports. We will add assign port, a lamp port, this way, and here is our Josephson junction. We can delete this, we won't use this trace. Here is our second port. We'll click add excitation port, lamp port, new line. So this is our trace. Our ports are assigned. And I think we can change assign material. We can change it to perfect electric conductor, or I think aluminium might be also the other option if we want to simulate it. But perfect electric conductor means that the chip is cooled down to preferred temperature, and it becomes superconducting. So this should be perfect electric conductor in our case, I think. Yeah, so perfect electric conductor. Now we will need to click add solution setup. We will click add auto, and we will do sweep from 1 gigahertz to 10 gigahertz, and we may choose 5000 in one, and interpolating. So this is our analysis. This is our new report for We can simply probably delete this and leave just a trace, because this is all we would require for our simulation. And now we can try to run validate and see if everything is fine. We have two warnings, which is um, um, which is new material is assigned for trace. And I think we can solve this by assigning material, which is perfect electric conductor. We can also use aluminium, but because aluminium is the metal for connections in quantum chips or in classical chips in general. But the problem with this is that once we cool the aluminium down to the temperatures we require for superconducting quantum computing, um, the material becomes superconducting, and thus we cannot use aluminium, but we will need to use perfect electric conductor since it is superconducting, right? Now we can run our validate check and see if everything is correct. We have one error, and this means no solution has been created. And also the boundaries, so we can delete one perfect electric conductor which appeared somehow. We can add solution auto 1 gigahertz to 10 gigahertz, and we can have 1 0, so it's 5001. Now we can click validate and we can see that everything is correct. So everything that is left to do is analyze and CR plot and our results. Oh, and that's a wrap. One more thing, if you have something to say, please feel free to contact me either on Gmail or LinkedIn. Thank you.